Swayam Prabha. Digital India. Educated India.
Okay, so also if you want to compare this with the book, I say which sections I'm covering, okay, so that you can go back and look at the notes. You can check, because I'm not going to be bogged down with the details. So we discussed in the previous lecture about scales, okay, and I also said that unlike classical turbulence, where all you have is your vessel, in this case the big bucket, okay, but in the case of multiphase flow, the good news is that there are other length scales, like you have particle diameter, and the interparticle spacing is a backhanded way of talking about volume fraction. Larger particle volume fraction, they are going to be closer. And if there are only few particles, then interparticle spacing will be large. And in the previous slide lecture, I talked about varying instabilities, okay. So if you have bands of particles, how thick are the bands? If the fingers are coming, are there dozen fingers? How thick are they? So in other words, there are some new length scale. Each finger may consist of million particles. So what you realize is that there are length scales coming naturally out of the problem. That comes from multiphase instabilities. So these are the dispersed phase length scales. And what I wanted to say, one thing last time I wrote this, is I want you to think about, even in a very dilute flow, particles aren't too far away, okay. If I say 1% volume fraction, phi d is the particle volume fraction, let's say is 1%, then the interparticle distance LD as a function of diameter is only 3.74. Therefore, if particles are there at 1% volume fraction, on average one particle and another particle are away only by 3.7 diameters, because it goes as to the power 1/3. The interparticle distance LD goes as volume fraction to the power 1/3. So if you make the volume fraction 0.1%, this may go to 5, something very. So in other words, particles are always very close to each other on average. That's one lesson I want to leave you with, even under very dilute condition. Therefore, particles will interact with each other, okay. And of course, continuous phase length scales, we all know in a turbulent flow you have Kolmogorov scale, energy containing eddy scales, big eddies that contain eddies, and system level scales, okay. So there are length scale galore, and there are also time scales, okay. Push, this is related to the question kind of what you are asking about, is that Professor Pushpavanam was asking, what about turbulence, and when you put particles, what happens? A lot of what the regime that I am interested in is, let's say you have a fluidized bed. Even if you don't have any particles at all, it's going to be fairly turbulent. If you just blew air in there, it's going to be pretty high velocity, okay. Or blood flow, even without red blood cells, will be fairly turbulent in your large arteries, not necessarily in your capillaries, fairly large turbulent. Certainly pipe flow will be turbulent under most conditions, okay. So this red line that you see is the, by the way, I didn't realize that I could draw it, so I brought here pre-drawn ones, okay. But tomorrow's lecture I will make some adjustment now that I know that I have a pen, okay. But let's go with this one. So this red curve that you see here is the typical turbulent spectrum, okay. So on the x-axis is the 1/length scale, which is wave number, and in the y-axis is the energy and everything in a log scale. And you all know you have the energy, this is k to the power minus 5/3 spectra and the exponential region, etc. Let's say you have a turbulent flow, classical turbulent flow, and let's say you put particles in there. Okay. So that's the kind of question that I want to ask. So what I want you to think in terms of is that first you want to say what is called globally undisturbed flow. Remove all the particles and ask yourself what the flow going to look like. It could be a laminar flow, or it could be already a turbulent flow. And then you add particles and then look at what happens. So in other words, there is a difference between single phase and the multi-phase. We now know how to handle single phase turbulence. You have lots of codes which will do that. And if you want to sort of use those ideas and want to deal with multi-phase flow, we want to know what are the differences so that we are able to capture all the important physics. Okay. Now first I want to talk about when the scales are separate. So in other words, the red spectrum is what I said is the classical turbulence, and this point is the 1/Kolmogorov scale. Now if the particle diameter and the interparticle spacings are all even smaller, so you have turbulent eddies, and let's say the turbulent eddies, smallest eddy is 1 millimeter, and all the particles are 50 micron and their separation is few hundred microns, any wakes or anything it's going to do is much smaller than the turbulence you already have. Okay, that's what is called scale separated problem. This is when you can say, oh, my particles behave sort of like molecules, they are below the turbulent eddies. Okay, so this is, I'm not saying it's easy problem, it's an easier multiphase problem. There is a clear separation. Without particles there is turbulence, and particles when they are added they are very small, they are creating their wakes, there is energy produced, and that is this little bump in there. So in other words, particles create some turbulence because of the random distribution, but the most difficult part is due to their presence, even the regular large scale turbulence is different. In other words, this red curve now suddenly becomes this yellow colored curve. So in other words, particles, why? Because these particles, just like you saw, was layered, they weren't, so they introduce new scales, they change everything, they damp turbulence sometimes. So here you can see, look at this point, the way I have schematically drawn, turbulence is damped, all the big scales are damped, and the small scales of the classical turbulence are augmented by turbulence. Now this could happen in, if you started with there is no red curve, it's a laminar flow. Laminar flow could be made turbulent by the presence of the particles. Okay, so there's a lot of interesting. So it could only be pseudo turbulence, or it could be classical turbulent modified. Therefore, when we model, we got to think in terms of, is my model take care of pseudo turbulence? Does my model take care of this yellow, this portion modified, particle modified turbulence? Am I taking care of it? Sometimes you say, well, pseudo turbulence is so small, why do I bother with it? I don't have to bother with it. Okay, those are the kind of stuff that you can make a call.
So this pseudo turbulence also we have initial subrange.
What is it?
In pseudo turbulence region case also we have initial subrange.
I cannot hear.
Initial subrange region.
No. I don't know. We don't know.
Like energy transfer takes place from larger eddies to smaller eddies in pseudo turbulence.
In this case, it is certainly highly dissipative, right? See, why did this red curve stop there? Because below that scale, the eddies Reynolds numbers are less than 1. Because the way you identify Kolmogorov scale is where turbulent Reynolds number becomes 1. Every scale smaller than that. So they will be highly dissipative. So all these pseudo turbulence will be dissipative here.
Red color I am able to follow. So the yellow color I had a small doubt and clarification.
it will be mostly dissipation dominated because of the range of scales in this case. But in the next one that I am talking about is when there is no scale separation, okay, where particles are as big as Kolmogorov eddies or even more, then particle generated turbulence can change your inertial scale dynamics. Okay. So, they create their own turbulence, which is sort of Trudeau turbulence, but they also modify the turbulence, and the whole thing could be much more complicated. So, this is a much harder problem when your particles are big. As we discussed, without particles it could be laminar flow or it could be a turbulent flow depending on your application, and when you add particles, at least this is how I would think what the particles are doing. Okay, sort of go step by step. First, think of these particles being point particles. So, what we do is mentally you shrink all the particles to a point, so they do not occupy any more volume. Then, but you preserve the mass of the particle. So, now what you have is a heavier fluid if the particles are heavy. If they are bubbles, then you have made the fluid lighter. So, I say, okay, if the particles do not have a volume, just by their mass they can change the fluid. And it gives rise to two effects. They are called inertia effect and buoyancy effect, body force effect, and they play a very important role. Say for example, in muddy river flows into ocean, the muddy water, the particles are very dilute, but yet it is maybe a fraction of a percent heavier than the surrounding fluid, and it makes a big difference, heck a lot of difference. Okay, and it creates extremely turbulent flows because the scales are very big. Okay, there when you model that, you want to ask what's the important effect in that flow. It turns out in that multi-phase flow the buoyancy effect becomes very large. Let us say you are sizing a pipe, a pump, and you want to pump a slurry. Maybe one of the effects that you have to think is, now you are pumping a heavier fluid. That is the inertia effect I am talking about, the fact that you have a heavier fluid. So, those are the easier mechanisms to think of. So, the fact that you have a multi-phase flow, you first want to think, what is the inertia effect, how heavy my fluid is because I have added things, and what is the effect of buoyancy. Say for example, you have, this is an experiment people do, there is a big tank and there is a muddy water on one side stopped by a gate, and they remove the gate and the heavy water flows out. Okay. So, that is the buoyancy effect, because heavier fluid, hydrostatic pressure increases faster than the lighter fluid. So, at the bottom high pressure, so it pushes and it wants to go. So, those are the two important effects that I would want you to think. Here there is nothing to do with the volume occupied by the particles. So, we have point particle, this is called dusty gas, this is just a terminology, that is a way of thinking. Okay. Now, you say, well, let me throw in my finite size particles, okay, that they occupy. But still we are saying, let us consider them. In the previous slide or in this slide also, I am still not letting the particles move different from the surrounding fluid. I am just saying, hey, they move with the fluid. Previously it was heavy, inertia was more, now they occupy volume. So, you have what is called a volume effect. More the particles in some finite volume, less the fluid there. So, in other words, a incompressible multi-phase flow may behave like compressible fluid, just because particles come and go, and if you take a finite volume cell, you are not guaranteed to have the same volume fraction of fluid and particles. So, it behaves like a compressible. That is called the volume effect. The other thing which is a little subtler effect is that viscosity is nothing but stress strain relation. So, in other words, you apply a certain strain and the stress associated with that. Now, when you put particles, the stress strain relation changes. just because the particles that occupies a volume, it imposes no penetration, no slip boundary conditions, and therefore the response to strain will be different. So in other words, the effective viscosity will be different, and that problem was solved by Einstein many decades ago. And the other problem is conductivity of a medium with holes or with some other particles, the effective conductivity also. Just like viscosity, conductivity changes, and that was solved by Maxwell, okay, long time ago. These are very somewhat easier problems, okay. But now what happens when you have random distribution of particles, clusters of particles, it gets really interesting, okay. But that's another effect, that effective viscosity, effective conductivity changes, and I call that thermodynamic and transport effects, okay. So we have now covered 4 effects: inertia effect, buoyancy effect, volume effect, and thermodynamic effect, okay. Now we go finally to the real problem, which is the multiphase flow. The particles are heavier and they occupy volume, and they move different from the surrounding fluid. So there is drag, lift forces. Their temperature may not be the same as the surrounding fluid. So this is what is called slip effect. Slip is just simply saying that particle properties and the surrounding fluid properties are not the same. Much of multiphase flow is interested in this mainly because you are talking about drag forces, heat transfer between droplets, or evaporation of droplets, etc. Why does a droplet evaporate? Because the mass fraction of whatever surrounding it doesn't match. So in other words, there is a slip, there is a difference. That difference gives rise to mass transfer, momentum transfer, which is drag, and energy transfer, heat transfer, okay. So all of them happens. So there are 5 so I call it 5 multiphase mechanisms, okay, and they become very important, and that's what is listed here: inertia effect, body force effect, volume effect, thermodynamic and transport effect, and slip effect. So if you keep that in mind, these are the 5 mechanistic ways by which a multiphase flow will differ from a single phase flow. Now you can add other things, electric effects and so on and so forth, you could add on top of that, but these are mechanistically the most important mechanisms in a multiphase flow. And I talked about some examples. So this hypopycnal flow that I talked about, this is basically a muddy river going into the ocean. And what happens is that if you look from the side, you will see these kind of settling of these heavier particles. In other words, it creates what are called double diffusive instabilities form. These are about centimeters in type, etc. The reason they are important, because one of the things that you will be interested is how fast these fine sediment settle down. It's a very important question for lots of people, okay. Now if you look at the settling velocity of an individual particle, you will be off by 100 times or 1,000 times, because these instabilities make these blobs go down 100 times faster than what individual particles falling down. So in other words, they matter, and what controls them. Now if you want to study this problem, do you need to worry about all these effects? No. You can make the problem much simpler. So earlier I started by saying one of the challenges in multiphase flow is that there is no one governing equation to solve every problem. You got to pick and choose what model that you want. The reason is you got to understand which of these 5 effects are important. In this problem you can ask which effects are important. Body force effect is really important, okay. It turns out the inertia effect is not important. Slip effect is important in the sense that these particles sort of heavier and they slip down. The other viscosity change is not important. This volume occupied by the particles is not important. So the governing equation you will choose is something that will preserve these 2 main physics that are important in this problem, whereas you could simplify the problem by not including the other effects. Okay, this is the kind of argument. So,
inertia effect. Can you just explain what you mean by inertia effect?
Yeah. So when you have Navier-Stokes equation, you have rho times acceleration is equal to body force, viscous terms, and so on. So I'm talking about the rho that multiplies the acceleration, the mass of the fluid. Okay. Now it's like the Boussinesq kind of argument. If body force effect is important, rho times g becomes important. The fact that you have slightly heavier fluid somewhere, lighter fluid somewhere, that creating this buoyancy force difference, thermal convection like effects will take place. Now the fact that the rho sitting in front of the acceleration term is very important if inertial effects are important. So when you are trying to pump fluid and the density of the mixture is heavier than the water, then you have now pumping a bigger heavier fluid. So in this kind of application, you just can deal with what is called the Boussinesq model, and I will talk about it later in, say, maybe Thursday or Friday. Okay. The body force and the density variation is important as far as body force is concerned when it's multiplied by g. Everywhere else you could consider the density to be that of water. So in other words, it is the density difference between the muddy water and the clear water is off by maybe less than 0.5%. But it makes a big difference as far as buoyancy is concerned, and that's what I meant.